The line between effective stormwater control and a costly disaster often depends on one crucial value: the time of concentration. It's the heartbeat of a catchment's response, the key to estimating peak flow, designing reliable drainage systems, planning flood warnings, and even predicting the first flush timing for stormwater quality management. By the end of this tutorial, you will know how to calculate the time of concentration through practical examples using key formulas. This includes a step-by-step walkthrough of the powerful kinematic wave method. Stay with me. The time of concentration is the time it takes for a water droplet that falls on the most remote points in the watershed to travel to the outlet or any point of interest. Time of concentration, or TC, has two major components: overland flow or sheet flow time and the conduit travel time through drainage conveyance assets such as gutters, pipes, or channels. We take TC as the critical duration of our design rainfall event. That will help us to estimate the maximum peak flow rate that a storm can produce in a catchment. The influencing factors on the time of concentration can be classified into two main groups: catchment characteristics such as length, slope, and land cover, and rainfall event characteristics such as rainfall intensity and rainfall temporal and spatial distribution. Since TC is a theoretical value, we must rely on estimation methods. These generally fall into two categories: physically based formulas and empirical formulas. To estimate TC, physically based formulas generally describe the flow of water using fundamental principles of fluid dynamics, such as the conservation of mass and momentum. Kinematic wave method is the best example of this group. It captures how water moves through a catchment by linking flow velocity, slope, roughness, and length of flow path into a single relationship. This can estimate the overland flow time. The key parameters are flow length in meter, slope, Manning's roughness, and rainfall intensity in mm per hour. The calculated overland flow time will be in minutes. Since rainfall intensity and overland flow time are related, the process of using this formula will be iterative. Empirical formulas, on the other hand, are derived from regression analysis of data from numerous catchments. They are simple, but their accuracy is limited to the catchments similar to those used to develop the formula. The most simplistic version of such formulas relate TC to the catchment area. They are generally developed for certain types of catchments and even climates, making them locally acceptable tools for a rough estimation of TC. However, in this tutorial, we only cover a few more advanced and famous empirical formulas as follows. First, the Kirpich Formula. This formula works best for natural catchments with well-defined channels where the catchment size is less than 80 hectares. The basin is assumed to have bare earth overland flow or flow in mouth channels. For other surface types, a correction factor will be multiplied by the calculated TC. In this formula, flow length L is in meter, S represents the slope, and the calculated TC will be in minutes. The second one is Kerby Formula. This one works best for catchments smaller than 4 hectares with a slope smaller than 1 person and a flow length smaller than 365 meter. This could perhaps work well in developed areas where such slopes are dominant. This formula uses the flow length L in meter, S represents the slope, and the parameter R represents something similar to surface roughness, as shown in the table below. The resulting TC will be in minutes. The last one is Bransby-Williams Formula. This one has been popular in Australia for nearly 100 years and was recommended by Australian Rainfall and Runoff Guidelines 1987 version. In this formula, L is the stream length in kilometer, A is the catchment area in square kilometer, and SE is the average stream slope in meter per kilometer. The calculated TC will be in minutes. It is worth noting that this formula yields a relatively faster time of concentration than the actual one. Our practical example is on this side that is shown. The area is 4 hectares, the flow length is 400 meter, the surface type is bare earth, and the Manning coefficient of 0.016 is assumed for that. And for the slope, the elevation contours are provided as you can see. The idea is to calculate time of concentration using both physically based and also the 3 empirical formulas that we learned in this tutorial. The first thing that we do is going to be calculation of the slope. The lowest and the upper point of the catchment has 120.5 and 122.5 divided by 400, which is the length, that will give me 0.005 as the slope meter per meter. The reason that we have chosen such a small catchment is for the sake of comparison between different models that we have learned today. So we start with the kinematic wave, which is the main one for us. The formula is written here. Since there is no information about the conduit flow, no pipe, no channel, so we can assume that our TC is basically all the overland flow time. And after that, we have another note about the fact that the rainfall intensity is involved in this formula, and that means that we are going to have an iterative process, and that's why we need to start with an assumed value for either TO or the rainfall intensity. I personally prefer to assume a number for the rainfall intensity. That will be easier to navigate in the IFD tables. So we also assume a frequency for our event today. We consider 1 in 5 years, because if I go to the IFD tables to pick up the rainfall intensity, I need to know for what frequency I want that. So that's why I assume I'm working on 1 in 5 years. So I go to the IFD table of my selected site. So we are not going to explain how you can access that. We have already covered it in a different video. So imagine that this is your table for your site. The values are in mm per hour. There are rainfall intensities for different durations and different AEPs. So in our case, we said we are after 1 in 5 years. That's why I'm working on this table that is highlighted in red color. So what numbers shall I pick from these intensities available in this block? I would say if you choose a very far value from the ultimate one, the number of iteration will be perhaps high. But if you guess it perhaps good, that will help you to have a less number of iteration. My general suggestion is to look into your catchment size. If it is a small catchment, you expect a small time of concentration, so it's better to choose your numbers from the top rows of this table. And if your catchment is huge, then you are expecting longer time of concentration, and automatically you should go for the intensities that come from the lower part of this table. In our case, I would guess that the values for my time of concentration should be in the scale of minutes, for example 5 or maybe up to maximum 25 minutes. So that's why I choose my numbers somewhere around that. So I would go for 60 mm per hour. I choose a round number, which is some between 10 to 15 minutes time of concentration. So having that, I put it in the formula. It's very simple. L is available, N is given, S we just calculated in the first slide, so we just put the numbers in, and I get my TC or TO at 20.1 minutes. That means that I need to go back to IFD and find the intensity. So this is my first iteration basically. So after getting my TC, I should go back to the table, and for the 20 minutes, the I value is 47.6. So now you can see my first guess, which was 60, is now getting corrected by the iteration. So now I'm getting a new I of 47.6. So I go to the next iteration. So that's what I'm going to bring to the iteration number 2. And I come here, I plug in the 47.6 into the same equation. All numbers are same, only I intensity is going to be different, and I will get a 22.1 minute this round. So that means that our second iteration is now completed. I go to the table, this round for 22.1, I fall between 2 rows. We don't have 22 in the table. So I need to interpolate between 47.6 and 41.7, which I have already done that here. And the answer will be 45.1. I bring it back, I just get it as my next I for the next iteration. So I go to the iteration number 3, I plug in 45.1 in the same formula, I get 22.6 this round, slightly higher. I do the same interpolation and I get 44.5. I didn't show the interpolation process just for this saving time. So 44.5, we go to the next. So I plug it in again and I get 22.7, and I can stop because very slight change in the TC. So that's the converged value after the iteration. So if you want to pick the numbers, your time of concentration is 22.7 minutes and your ultimate I is going to be 44.5 mm per hour. So we are done with kinematic wave. Now we move to Kirpich formula. It works only with length and slope. So we just put the numbers in. I get 14.7 minutes, much smaller than what kinematic wave gave to us. And the reason for that is that this one doesn't consider rainfall impacts. And also be considered that the roughness was hidden in correction factors. But since we assume the bare earth land, no correction factor is multiplied. We go then to Kerby formula. For this one, we need L, S, and R. R works for surface type again. And here, as you can see, for the smooth bare soil, we are expecting 0.1. None of the other numbers matches what we have. So I'm going to consider R of 0.1 in my calculation. I plug in numbers and I will get 27.8 minutes. Again, be considering that rainfall impact is ignored. And finally, Bransby-Williams. In this formula, we have area should be in square kilometer. That's why I've converted hectare into a square kilometer. Length should be in kilometer. Again, by dividing by 1000, I have got 0.4. And finally, our S. If you remember, SE is in meter per kilometer. So a conversion is needed here. So if you remember, we had 2 meter difference in height between the lowest and the highest point of the catchment within 400 meter length. Dividing 2 meter over 0.4 kilometer, I get 5 meter per kilometer, which will be my SE or average stream slope. And I plug it into the formula, all the numbers as I said, and we get 23.2. Be careful that roughness and rainfall impacts again are ignored in this formula. So if I compare, the lowest value came from Kirpich, after that kinematic wave, then Bransby-Williams formula, and finally the Kerby. 2 points for you to consider. Ignoring rainfall intensity is one of the major drawbacks of the empirical formulas. And the second point is that we assume the very small catchment. That may not be an ideal case for some of the models that are basically developed for large catchments. So we need to be careful about it, meaning that if we choose too small or too large catchments compared to those that have been used to develop a formula, may affect the accuracy of the results that we get from them. And finally, I want to show a bit of sensitivity test. Based on the formulas that we have, in all of them, slope, if you check, you will see that it has a kind of inverse relationship with TC. So if I increase the slope, TC will reduce, which means it is basically related to the velocity. So having a larger slope creates larger velocities of flow, and that means that the time of concentration reduces. If we go for flow length, obviously longer pathway gives us a longer time of concentration, and roughness, if increases, will also create a longer travel time or time of concentration for us. The question is, what about the rainfall intensity? The only formula that has it is kinematic wave. It's in the denominator, and it's quite obvious that basically by increasing the intensity, we are expecting to have a reduced time of concentration. But in order to have a bit of idea how it works, I want to show it by an example again with the kinematic wave method. So what we do this round, I move from 1 in 5 year event to 1 in 100 event. And that brings me to the last column of this IFD table. And if you compare, you will see that relatively all the numbers in this column are larger than the previous one that we used. So that means that I'm increasing the rainfall intensity. And now I want to see the impact of it on our time of concentration. So the same process, I start with 100 this round because all the numbers are big in this table. So I start with a random number of 100, which is giving me 16.5. Be careful that nothing has been changed except I. And this 16.5 will be my first value. I go to the table, I will fall between 15 and 20 minutes. And that means interpolation is needed. I have done that. I've got 106. and I bring it back here, I'm ready to finish my iteration 1 and move to iteration 2. So using 106 mm per hour and plugging it into the formula, I get 16 minutes this round. And again, by interpolation, which I haven't shown here for saving time, I get 107.7 mm per hour. That's the end of iteration 2. I go to iteration 3. I use that one, put it in the formula, I get 15.9, and I will stop here because 16 becomes 15.9. It's a very minor change in the time of concentration, and we can conclude the calculation. So by comparing the numbers that we have got, you can see that in the case of 1 in 5 years, the TC is 22.7 minutes. And in the case of 1 in 100 years, the TC will be 15.9, smaller. So you can see that by increasing the intensity, we have a smaller time of concentration. Be noted that the final TC and its corresponding rainfall intensity can be used for your peak flow calculation, because these are what we call the critical event. The critical event is the one that can produce the maximum flow in our catchment for that specific duration and frequency that you have chosen. For example, if you're playing with the rational formula, you can adopt the final I or rainfall intensity that you have got and put it in the formula of Q equal to CIA in order to get your peak flow out of that. Understanding how the time of concentration changes with catchment slope, size, or vegetation cover, or the rainfall event properties is crucial. In our next video, we will take this a step further with the catchment response sensitivity analysis using the RORP, a hydrological model, showing how these factors can reshape the runoff hydrograph. This will give us powerful insights for flood planning and risk assessment. Stay tuned.